In this lesson, we're going to be looking at solving systems of linear equations that have three equations with three unknowns. Now, when it came to two equations with two unknowns, we visualized what was going on by graphing two lines and looking for their point of intersection. But if we have three unknowns, that means that we have an equation that has x's, y's, and z's in it. So we have to understand what that looks like. So we're going to go ahead and look at a couple different graphs and what it's going to look like to have an entire system of three equations, three unknowns. What I have graphed here is the equation x plus y plus z equals 1. In three dimensions, what that looks like is actually a plane. So ignore the fact that this kind of looks like a kite in that direction. What's actually going on is in each of those directions that are flat, it actually extends out to infinity. So this is actually a plane that extends out in all directions. So a single equation with three variables in it is going to be a plane. You can think about this like a piece of paper that extends out in all directions. So now I've added a second plane. So now I have negative x minus y plus z equals 1. So now we have these two planes that are intersecting. If I look from this direction, they sort of look like an x. Now, if we look at what their actual intersection is, it looks like they're intersecting at a line is where they're actually intersecting. So there's still an infinite number of points of ordered triplets in three-dimensional space here where they intersect. So this would be two equations that have three variables each, and they're intersecting at a line. What we want to look at then is to say, well, what happens if I introduce an entire third plane into the mix? Where do they meet at? So if I introduce a third plane into the mix, if we want to look at where they all three intersect at, it looks like right up there in that little crook over there, there's a single point that all three planes intersect at. So if we have three equations with three unknowns, then what should happen is they should intersect at one individual ordered triplet at one point in three-dimensional space. But there are some weird situations that can come up. And that's what we want to look at so we can start to understand. We know the weird situations in two dimensions. In two dimensions, the weird situations are either parallel lines, which means there's no solution, or the two lines were the same, meaning infinitely many. Let's look at a couple weird situations here. So here's one weird situation that can arise, and this is hopefully an obvious one, where we have three planes that are parallel. They're never going to cross, and so this is a situation where there's going to be no solution. Now we can have another interesting situation that's similar. We could have two planes that are parallel and one that's not. And so it intersects both of the parallel planes, but if we want to answer the question of where all three of them cross at, they don't. So this would be another situation of no solution. Now there's even other ways to get no solution. We can have this situation where they almost form like a tent in the middle. There's a little triangle that goes on forever. What's happening here is these two planes have a line of intersection. The other two planes there have a line of intersection. This plane and that plane have a line of intersection. And all the lines of intersection are parallel to each other. So where do all three of these meet at? They don't. So again, here's another weird situation. One of the reasons I want to point out some of these weird cases is when it comes to three equations, three unknowns, our no solutions aren't always going to be obvious. So it's not like all the numbers are the same except for maybe the constants. They might look completely different, like in this one here. As we can see, they don't cross anywhere, but yet they're all very different planes. They're not parallel. They're just different planes that happen to not intersect. Now we can also have an infinite number of solutions. There's the obvious infinite number of solutions where all three planes are stacked on top of each other. But I want to point out that there's some other ways too. So here's a way that we have an infinite number of solutions when all three planes intersect on the same line. So this is a situation where they're actually very different planes, but there's still an infinite number of solutions. And so they meet in a line, and all we can really say there is there's an infinite number of solutions. Now here's yet another way that we could have an infinite number of solutions. Here I've got two planes that are the same and one that crosses them. So that can get us an infinite number of solutions as well. But with all of these said, there's one last one that I really want to talk about that's really important for our overall understanding. And that's to say, what if two of them are the same? We'll say z equals 0 and z equals 0. And what if the other one is parallel to them? There's no solution there. And I want to point that out because the first two were the same plane on top of each other. So in terms of equations, this might seem like an obvious, I look at the first two equations and they're identical to each other. And we want to automatically jump to say there's an infinite number of solutions. But that's not necessarily the case because if that other one's parallel, there could actually be no solution. So the moral of the story here, I'm going to go through a process of how to solve a system of three equations, three unknowns. And it's an algebraic process. During that process, we don't want to stop all of a sudden and say, I think I know the answer here. We're going to go through with the process. And we're going to keep in mind that no solution trumps infinitely many solutions. If anywhere in the problem we get no solution, that's when you can stop and say, yep, there's no solution, I got to a wacky case. But if you get infinitely many, you've got to keep on going with the problem until you get to the point that, all right, I'm sure it's infinitely many, and I'll tell you how to get there once we start going over the algebraic process. Or else, maybe we got to say, oh, hold on a second, I got a no solution, that trumps it. The answer is no solution. So we're going to go through the process here as we move forward. But I wanted to just show you these so you can kind of visualize what's going on as we're solving these problems.
So as we look at solving systems of three equations, three unknowns, I want to list out the steps to handle that. But before we actually look at each individual step, and then we're going to look at examples of these, I do want to remind you of big picture what's going on here. Just like when we dealt with two equations, two unknowns, the goal is to do something algebraically to make the problem simpler, to get rid of one of the variables in one of the equations. So overall, what the big picture is here is we're going to look at a strategy on how we can go from having three equations with three unknowns down to having two equations, two unknowns. And if we can look at that as the only new thing in this entire lesson, then once you get down to two equations, two unknowns, you just use what we learned from the last lesson. And you solve that system of two equations, two unknowns. And that's going to get you to your answer. And that's basically what these four steps are. So these four steps are going to lay out how to go through that process. Now, as we move forward through here, and I'm going to demonstrate this on one of the first examples, I'm going to highly advise that we always use the addition method rather than the substitution method. The substitution method works, it's legal, there's nothing wrong with it, but when it comes to three equations, three unknowns, to put it bluntly, it gets messy. The addition method takes a little more planning and a little bit more thought, but the work is so much simpler. And so that's going to be our game plan, because what I've seen from my experience in teaching is that the more steps that we do, the more opportunity there is to make an error. If we can condense our steps down to be as efficient as possible, we're less likely to make errors. So that's why I want to approach this from the addition standpoint and kind of ignore substitution in this lesson. So let's talk about these four steps. So I told you that we're going to try to eliminate one of the variables. We're going to try to take this three equation, three unknown system and break it down to two equations, two unknowns. And so the very first thing I want you to do is to determine which variable it is that you want to eliminate. And I want you to literally write it down, and we're going to practice that in all of our examples. And we're going to say, all right, let's eliminate x or y or z, whatever it might be. And we're going to look at some strategies through the examples on what's going to be a smart variable to eliminate. So we're going to look for one, first of all, that's already eliminated from one of the equations. That's going to be what I call a freebie, because that's going to give us an equation that says, all right, well, this variable is already missing from here. That's pretty sweet. So we're going to look for that first. We're going to look for a freebie, but no matter what, we're going to determine which variable to eliminate. Step 2. So we're going to eliminate that variable in two different ways. Each time we eliminate it, we're going to get an equation that has the remaining two variables in it. And so our goal of this step is going to be to end up with two equations that have the same two unknowns. And that's really important. We don't want to have one equation that has x and y and a different one that has x and z, because then all of a sudden we still have three variables, and that's not helpful. We want to have two equations with two unknowns. So we're going to eliminate that variable that we chose in step 1 in two different ways. In doing so, we need to use all three equations. We're going to be using the addition method to do this. So maybe we're going to add equations 1 and 2 together. That'll get us one equation. And then maybe we'll use 2 and 3, and that'll get us a second equation. Or maybe we'll use 1 and 3 and 2 and 3. It doesn't matter which ones we use. What matters is that we eventually use all three equations and that we eliminate that same variable in two different ways. So that's what we want to pay attention to, and we'll make that point as we look at each of the examples as well. Once we have two equations with two unknowns, we're just going to solve it. We're going to get two answers. If it was x and y that we had, now we know what x is, we know what y is. And so once we have those two answers, step 4 is to take those two answers and plug them back into one of the original equations and find your third variable. Now, we could throw step 5 in here and say check your proposed solution. Wouldn't be a bad idea. And just like with systems of two equations, two unknowns, where you had to check in both of the equations to make sure your solution worked, with three equations, three unknowns, you better check your solution in all three equations to make sure it works. Because going back to the big picture of these being planes and it's where they're intersecting, if you only check on one of the equations, you're only seeing if that ordered triplet is on one of the planes. We want to make sure it's on all three. It's where they intersect at. Last thing I want to talk about as far as general overview before we get into the individual examples is that we also do write these as ordered triplets, meaning we have parentheses and then it's x comma y comma z. All right, so here's a system of three equations, three unknowns. We want to solve this. Step 1, we need to determine which variable it is that we want to eliminate. Now, if we go back through your 4 steps, I had said to look out for freebies. Look for an equation where there's already a variable missing. So I want to point out what's going on here is that we do have a variable missing there. We also have a variable that's already missing there, meaning the smart choices for which variable to eliminate are either going to be x or z. We're not going to eliminate y because it's not a freebie. Even though it might not be hard to eliminate the y's, it's not free, and free is always better than easy. So we're going to pick either x and z. To determine which one we should do, what I would suggest doing is looking at the remaining x's and the remaining z's and see how hard would it be to use the addition method to get rid of them again. So as far as the x's are concerned, I'm going to look at the remaining 7x and x and say, hey, that's not too horrible. I'd have to probably multiply by -7 in the second equation, and that would get them to line up nicely. But if I compare that to my z's, they're already set up to eliminate. So it looks like there is a smartest one here. And big picture here, always take a minute to make a plan up front. If you can save yourself work in the long run by planning your work out smart, you're going to be happy with yourself. So we're going to make a note to ourselves. You have a spot in your notes for this, but I'm always going to write it down, that we are going to eliminate z. It's important to write this down somewhere. Now, also as far as your organization, you're always going to make yourself a note that you're looking for two equations. I like to use a little bracket here if you want to use braces or whatever. It doesn't matter. Make some sort of notation that your goal is to end up getting two equations that are both missing z. Now, what I like to do personally as far as organizing my work is I like to keep the flow of the problem in one column here. So this is the flow of the problem. And then off to the side over here is my scrap. That's how I like to organize my work. And if I organize it the same way every time, then I'm not going to get lost in my problem and say, where am I at again? Also, if I make errors, it's easy to go back and follow my work and say, all right, where to make an error? And I can actually follow step by step by step. So I always follow the same pattern, and this is the pattern, and I'd advise doing it. So as far as the flow of the problem, these are our main steps where we say, all right, I'm supposed to eliminate z. I'm going to take my freebie first. I'm going to copy down equation 1. So copying down equation 1, that's one of my equations that's missing z. My goal is to get 2 equations missing z. So the next thing I need to do is eliminate the z's in a different way, which is going to happen from adding those two together. So off to the side in my scrap paper land, I'm going to rewrite that equation, and when I add them together, what am I going to get? I'm going to get x minus 3y equals 5. And I'm going to copy this over into the flow of my problem. And I'm going to pause for a second here. If we look back to our 4 steps, we have now determined which variable to eliminate. That was step 1. We've now eliminated that variable in 2 different ways. So if we look at where we're at now in this problem, what we've already accomplished is the only new thing to this entire lesson. So if we look at this right now, we can say, hold on a second. We've done problems like this before. This was last lesson. This is 2 equations, 2 unknowns. I know how to handle this. I'm going to multiply by -7. So I'm going to copy down the first equation there. But then if I multiply by -7, I get -7x, 21y equals -35. I add these guys together. That gets me 25y equals -25, or y equals -1. Now I need to continue solving my 2 equation, 2 unknown system. So what I mean by that is my eyes are still here. I'm ignoring everything else. I'm ignoring the work on the right. I'm ignoring the original problem. I'm focused on getting my 2 answers to the system of 2 equations, 2 unknowns. So what I'm going to do is I'm going to take that answer of y equals -1, and I'm going to plug that back into the blue equation there. That's going to get me x minus 3 times y equals 5, or x plus 3 equals 5, or x equals 2. So as far as our 4 steps, we're now done with step 3. We've finished solving the 2 equation, 2 unknown system. So now that we have this, now we can figure out what z is. So we look back to the original problem and we look for one of the equations that has a z in it. Doesn't matter which one, and we're going to plug back into that. So if I plug back into the equation that has z in it, that would be y minus 2z equals -1. If I add the 1 to the other side and then divide by -2, I find that z is 0. Now to write my final answer, the order matters because it is an ordered triplet. I'm going to have my x value, followed by my y value, followed by my z value. And that's the final answer to this question. All right, second example. For second example, we're going to start off the same way. We're going to start off choosing a variable to eliminate. Now, z seems like a reasonable possibility because we do have a freebie there. Y would also be a reasonable possibility because we do have a freebie there. X would even be a reasonable possibility because we do have a freebie there. So as we compare which one to do, I would notice that my z's have the same value. They need to become opposites, so not a huge deal there. The y's, well, I'd have to multiply by -4. The x's, well, I'd have to multiply by -2. I'm thinking the z's are probably the best bet. Now, I do want to point out that there's not a right or wrong answer here when you're making a decision on which variable to eliminate. Now, there might end up being an easier way, and you might pick wrong, and that's okay. But take the time to at least try to optimize your work. So we're going to try to eliminate z's. We're again going to make this notation here that I'm going to try to get down to 2 equations, 2 unknowns. That's my goal. I'm going to copy down the freebie. So I have one equation here that's already missing the z. Oops, not -1. I don't know why I copied that down. Helps to write down the right thing. Now let's look at the other two equations. I need to somehow get rid of the z's from them. So the best way to do that is going to be to multiply one of them by -1. So that means off in scrap paper land, I'm going to copy down that original second equation. In the original third equation, I'm going to multiply by -1, giving me -y, positive 4z, and positive 3. Once I add that together, I get 4x minus y equals 2. And I'm going to copy that over here into my two equation, two unknown spot. Because now I'm going to pause again and say that was the only thing new to this lesson. Now I'm back to two equations, two unknowns. At this point, I'm going to ignore everything else over here. All that doesn't exist. All that exists now is the two equation, two unknown system that I want to solve. So I'm going to look at that and say I can eliminate the x's or the y's. Doesn't really matter. I'm going to say let's choose the x's. Why not? We'll multiply by -2 in the top equation. That's going to make him look like -4x minus 8y equals -2. I'm going to copy down the second equation. That way I'm keeping my two equation, two unknown system together. I'm going to add those together. -4x and 4x is 0. I'm going to get -9y equals, well, 0. So that's pretty nice. Y must be 0. Remember, we're going to keep on solving the two equation, two unknown system. So now I need to find x. Our two equation, two unknown system had x and y, and I already know what y is. So I'm going to plug this back somewhere else within my two equation, two unknown system in order to get the x. So that's 2x plus 4 times 0 is 0 equals 1. So x must be, 1/2. That's all right. We can have a fraction. Now that we're done with our two equation, two unknown portion of the system, now we want to find the third variable. We're looking for z. We have x and y already. So we look back to the original problem and look anywhere up there for a z and plug in the necessary variables to solve for it. So I'm going to go back to the original second equation where we had 4 times x minus 4 times z equals -1. 4 times 1/2 is 2. If I subtract the 2 to the other side, I get -3. And dividing by -4 gets me 3/4. So if I write this now as an ordered triplet, I'm going to have 1/2, 0, 3/4. Now this fraction answer, I'm probably going to want to check my answer on this one. So let's go ahead and get out our handy dandy calculator. And let's talk about checking our answer. What I would suggest doing for checking your answer here is to actually use the variables in your calculator. And you can do this with the graphing calculator or with the scientific calculator. I'll go over that in a second as well. We're going to convince the calculator that the x value is 1/2 by typing 1/2 followed by store, which is right above on. And then I'm going to type x by doing alpha x. Enter. I'm going to convince it that the y value is 0 by doing 0 store alpha. The number 1 has the y there. So we've stored 0 into y. And then I'm going to store 3/4 into z. In doing this, I'm going to go ahead and scroll back to my original problem now. This is going to make checking our work a lot easier because now I can just type the original problem of 2x plus 4y. When I hit enter, I'm hoping to get 1, and I do. So then I check the second equation of 4x minus 4z. I'm hoping to get negative 1, and I do. Then I check the third equation by doing y minus 4z. I'm hoping to get negative 3, and I do. So this does check out. I get the right answer here. So let's talk about doing the same thing with the scientific calculator. It's going to flow pretty much the exact same way, so I'm not going to go through all the steps. But I do want to point out, though, that if we do 1/2 and then store is just above on again, the x in this case is right above store. We hit that once, we store it for x. Now when we try to store for y, when we hit the variable once we get x, but if you hit it again, you get y. And so we can do the same thing for the z. We can type 3/4, and then we can store that. To do z, hit that button 3 times. And then same thing for retyping it. So we can retype it by doing 2x plus 4y, and we should get 1, and we do, and you can go through the next 2 equations as well. So now in this example, we're going to do one that does not have any freebies. Steps stay the same, we just don't have a freebie to start off with. We're still going to start off looking at which variable it is that we want to eliminate. So as I look at this guy, I start off with the x's, and I want to say, how hard would it be to eliminate the x's twice? So with the first and the third equation, I would need to multiply one of those guys by -1, and then I have to multiply one by -2 to get rid of the second one. That's not horrible. Let's see if there's any easier. We'll look at the y's. Well, the first two are set up for elimination already, so that's not quite a freebie, but it's pretty darn easy. So y's are kind of winning so far. And then same thing, you got a 2y in there, we're going to have to get one of our other guys up to a -2y. Not too shabby. If we look over at the z's, z's are very similar to the x's. For the first two, I'm going to have to make one of them the opposite. So I think I'm leaning towards the y's because of the fact that the first two are set up. It's not free, but it's very little work. So I'm going to make a note to myself that my goal is to eliminate y's. And I always make this note because with this 2 equation, 2 unknown system, I don't want to get lost and say I eliminated the y's for the first equation, but then I eliminated the x's for the second equation. I write this down so I can always remind myself, oh yeah, I'm trying to eliminate y's. So, off to the side, I'm going to do my work. So, one of my pieces of work is to use equations 1 and 2. So, I'm going to copy down equation 1. I'm going to copy down equation 2. It's not always equation 1 and 2. We just have to do this in 2 different ways. I'm choosing 1 and 2 because of the fact that the y's look so easy. So, if I add these together, I end up with 3x plus 2z equals 9. I'm just going to jot this over into my area for my 2 equation, 2 unknown system. And there's one of my 2 equations. Now, I've already used equations 1 and 2, which means I need to somehow use equation 3. Since I'm trying to get rid of the y's, I need to make sure I get rid of that 2y. So that's what I'm focusing on, is making sure that I can get rid of that 2y there. So in order to do that, maybe I multiply the second equation by 2. That'll bring him up to a -2y. Now I could have multiplied the first equation by -2. That'd work as well. There's no right or wrong way here. What is important is that we end up using all 3 equations. We can use the same equation twice. So, in multiplying that second equation by 2, I get 4x minus 2y plus 2z equals 6, and I copy down the original third equation. And then I'm going to add these guys together. That gets me 5x, 5z equals 20. Now I could go ahead and write this over my 2 equation, 2 unknown system, but I'm noticing that everything in here is divisible by 5. So before I write that over, I'm probably going to try to make my numbers smaller. And I'm going to say, let's divide both sides of that equation by 5. And it becomes x plus z equals 4. Now my numbers are a lot smaller, easier to work with. Always a good idea. So coming back over here, we've got ourselves x plus z equals 4. This is where we pause, we take a breath. This is the new material. We're done with the new material. Now we're back to 2 equations, 2 unknowns. We focus on just this 2 equation, 2 unknown system, and we solve it. So I'm going to go ahead and now try to eliminate, I think the z's probably. I'm going to multiply the second equation by -2. So I'm going to copy down the first equation. And then I'm going to get -2x, -2z equals -8. I'm going to add those together to get x equals 1. I'm going to finish solving the 2 equation, 2 unknown system by plugging this x equals 1 back into one of the equations from the 2 equation, 2 unknown system. That's going to give me 1 plus z equals 4. If I subtract the 1 to the other side, I get z equals 3. Now I need to solve for y. I have the x and the z, and I need the y. So I look back to the original system, and I look for which equation looks like it would be easiest to solve for y. I notice that I have a y with a coefficient of 1 in the first equation, so I'm liking the first equation. So that means I'm going to plug z equals 3 and x equals 1 into that equation. So I'm going to replace the x with a 1, I'm going to replace the z with a 3, and I'm going to solve that equation. 1 plus 3 is 4. Subtract the 4 to the other side gets me 2. Now that I have all 3, I can write an ordered triplet. The x value is 1, the y value is 2, and the z value is 3. So there's my answer, 1, 2, 3. So if we look big picture at this, we chose the variable to eliminate. Then, off to the side, we did some scrap work to eliminate that variable in 2 different ways. That resulted in 2 equations, 2 unknowns. We then solved the 2 equation, 2 unknown system. And then we took the answers from there, plugged them back into the original to get our third answer. And those are the basic steps that we can always follow in every system of 3 equations, 3 unknowns. Now, before I release you to work on your practice problem for this one, I do want to point out that after your practice problem, I'm going to go ahead and show you how this one would work with substitution, just to show you you don't want to do it. And in doing so, I want to point out that this whole process, this entire problem fits on one screen right here. Not too shabby. All right, we'll come back to talk about the substitution method. You don't need to take notes on this. This is where I'm just going to walk you through how this would work if you did want to do substitution. And again, we don't. So if you did want to use substitution, we would solve for one of the variables. So for instance, we would pick this equation and we would solve for x and say x equals -y minus z plus 6. So we subtract the y, subtract the z to the other side. Then in order to get 2 equations, 2 unknowns, we plug this into both of the other 2. So this is our 2 equation, 2 unknown part, where we're going to have 2 times -y minus z plus 6 minus y plus z equals 3. Then in the other equation, we're going to have negative y minus z plus 6 instead of the x, plus 2y plus 3z equals 14. Now we need to simplify this a bit. And so now I need to distribute the 2 in that first one. That's going to get me negative 2y minus 2z plus 12 minus y plus z equals 3. And in the second one, we can remove the parentheses and just copy everything else down. All right, so now I'm going to combine like terms. You'll notice that we're already scrolling. So with the y's, I've got negative 2y minus y is negative 3y. Negative 2z and positive z gets me negative z. Plus 12 equals 3. Second equation, combining like terms, I get y. I get plus 2z plus 6 equals 14. Now we're going to go ahead and throw the constants to the other side so that I have negative 3y minus z equals negative 9. And y plus 2z equals 8. All right, so now we're down to 2 equations, 2 unknowns. I'm going to zoom out a little bit just to point out the big difference here. When we did the addition method, we required just the couple steps of adding equations together. That's a lot of steps there. Let me zoom back in here to continue our work. So now if we were to continue doing the substitution method, we'd probably solve for y in this one, getting us negative 2z, oops, not equals, sorry, negative 2z plus 8. We'd plug this back in over here. That's going to get us negative 3 times negative 2z plus 8 minus z equals negative 9. Distribute. Combine like terms gets us 5z minus 24 equals negative 9. Add the 14 to the other side, or sorry, add the 24 to the other side. That's going to get us 15. Divide by 5, z equals 3. Now that we have z equals 3, we could start back substituting. We can get our y there, come all the way back up to the top to get the x. So we could plug the z up there and whatever we get for y up there. But you can see it's a whole lot of work here. A lot of places for error, a lot of places for sign mistakes. And that's really what I see, like with the distribution going on over here. I'm seeing sign mistakes and then the combining like terms here. So the moral of the story is I would not advise doing the substitution method. And that's why I'm teaching the addition method. And that's why I don't even want you taking notes on this. But I did want to show you just so you can say, yeah, it could be done. It's mathematically possible, but let's just not do it. So we're back to an example that has a freebie. So we should notice there is a freebie over here in the x's. You'll see why in a second that I'm giving this example later, that it is a little bit trickier, weird situation. But we're going to make our note to ourselves that we're going to eliminate x's. We're going to make our little note over here that we're going to end up with 2 equations, 2 unknowns. And we're going to take our freebie. So we're going to copy down equation 1, that's the freebie. And now we're going to eliminate the x's in a different way. So we're going to look at equations 2 and 3 and say, if I multiply by negative 1 on that second equation, that looks good. So let's come to scrap paper land over here. We're going to distribute the negative across that second equation. We're going to copy down the third equation. And then we can add them together. That's going to get me 5y minus 7z equals 20. Now you're probably saying, ooh, something looks funky. It sure does. We've got the same coefficient of y, the same coefficient of z, but different numbers on the other side over there. You might be able to start jumping to conclusions right now. I'm going to go ahead and finish this out because I want to get down to the point that we have something that we kind of know how to get to the answer from. So I'm going to go ahead and multiply the second equation by -1 in order to eliminate one of the variables. It will actually end up eliminating both, but that's okay. So if we copy down the first equation, distribute the negative on the second equation, then add these guys together, 5y minus 5y is 0. 7z minus 7z is 0. -20 plus 14 is -6. I have determined that 0 equals -6. That's not good. 0 doesn't equal -6. So this is going to be a no solution situation because that's not true, and there are no values of x, y, or z that will ever make it true. So we know it's no solution, so in our homework system, of course, we're going to answer that as does not exist. But here we're saying no solution to this system of equations. Now remember, we went through in the introduction to this that we want to be careful about infinitely many solutions. If we get infinitely many solutions at one early step in the problem, we got to continue on until we're down to where we're at now. So basically, if we would have got something like 0 equals 0 up here, then we still want to find the second equation. Because if the second equation is 0 equals 1, then the answer would be no solution. Because no solution trumps infinitely many solutions. But if we got something like 0 equals 0 and 0 equals 0 there, then we know that that's going to be infinitely many solutions. All right, let's take a look at example 5 now. So we're back to no freebies in this one. So we got to decide which variable to eliminate. So as I'm looking at my different variables, things that jump out at me, those x's don't look bad, but the 7 looks kind of ugly. It's going to be kind of tough to get rid of him. As I look at the y's, I do notice that the 2 and -2 work out really nicely. Not a big fan of the 9, but I can deal with it at least. Now, as far as the z's, everything's ugly over there. I'm not a big fan of anything going on over there. So I think because of the fact that the y's at least had one really easy option, I think that's the choice I'm going to make. I'm going to make my choice to eliminate the y's. And like always, I make my note that I want to end up with 2 equations out of this. So now off in scrap paper land, we're going to look at those 2 ways. Now one way is I'm just going to add together the first and third equation. Now I would highly advise actually rewriting it. You want to see this work somewhere on your paper so that if there's errors anywhere, you have a way to look back at your work and find those errors. So I'm copying this down. And then I'm going to add those 2 equations together. That's going to get me 4x 12z equals -20. And this is another one of those situations that everything here is divisible by 4. And so I'd probably do that in this step, is I would say, let me go ahead and divide everything by 4 before I write it over there into my system. So that's going to give me x plus 3z equals -5. Just making my numbers smaller. In the long run, that's generally going to be a good thing. So we've got ourselves x plus 3z equals -5. There's one of my 2 equations that are missing the y. And remember, that was my goal, was to eliminate the y's. So we're partway there. We used equations 1 and 3. So now we need to make sure that we use equation 2. So we need to somehow get rid of that 9y sitting there. So I'm going to have to build him up to 18, I think. So to do that, I'm going to multiply the second equation by 2. In order to eliminate that 18, I'm going to multiply this first equation by 9, because I noticed that the y's are already opposite signs. I could have multiplied the third equation by -9, but I'd prefer to not have to multiply by a negative. I'm less likely to make sign mistakes that way. So is I distribute the 9 across the first equation. That's going to give me 63x minus 18y plus, holy cow, a big number. So let's see, that's, let's get out a calculator just to make sure. I don't want to be making mistakes in this video and have to re-record the video. So let's go ahead and look at 19 times 9, 171 there. That's kind of a big number, but I want to pause for a second here and point out too, though, we can expect really big numbers when doing these problems because we are multiplying an entire equation by a value, then we're going to add this to another equation. So it's kind of actually normal to end up getting really big numbers when doing these problems. So don't freak out too much until your final answer is something really wacky. So we got negative 369 as what we're equal to. So again, big number, but that's okay. Now we're going to distribute the 2 across that parenthesis, getting negative 12x, positive 18y, negative 18z, and then 57 times 2 gets me 114. We're going to add these two equations together, and yeah, those numbers are big, but we can use calculators whenever we want, so that's all right. We're going to get 51x. The y's add up to 0. Now let's go ahead and use our calculator just to make sure over here on our 171 minus 18. We got 153 for our z's. And again, even though this isn't a horrible addition here, let's go ahead and use calculator. We got negative 369 plus 114. That's going to get us negative 255. All right, very ugly numbers, I know. But it looks like 51 actually divides into each of these. So just like we divided by 4 over there in our blue situation, we can divide by 51 here. That's going to get me x plus 3z equals negative 5. And as I write this much simpler thing over here, all of a sudden you can probably see what's going on. Now that we have the same two equations there, this is going to be an infinitely many solution situation. Now we can fully convince ourselves of that if we multiply by negative 1 on the second equation. So we get x plus 3z equals negative 5. Negative x minus 3z is positive 5. Add these together to get 0 equals 0. We have infinitely many solutions. Now let me try to explain in words what's happening here and how that relates back to our lesson intro. When we're getting two equations, two unknowns, what's actually happening here is we're looking at the intersection of two planes for each of those equations, and we're saying, if I just looked in the xz plane, what does the line of intersection look like? So as far as the blue situation, which the blue situation was planes 1 and 3, we see what his line of intersection looks like. Then we look at planes 1 and 2, and his line of intersection is the same. So what that tells us is all three planes share a line of intersection. So all these are intersecting on the same line rather than the same point. That's what's going on here. Now we don't really have to fully understand that as much as knowing if you get 0 equals 0, that's infinitely many solutions. And we're okay with that being the final answer. When it comes to three equations, three unknowns, I'm not going to ask you to write set builder notation. And remember, that's the notation. That's the set of all ordered triplets x, y, z such that something. Because of the fact that we're not going to take the time to describe or to understand, when we're getting infinitely many solutions because the three planes are the same plane, or when they're intersecting on the same line, or when two of them are the same plane and one is intersecting at a line. We're not going to take the time to look at all those different situations. So we're okay with saying infinitely many solutions. But be careful here because, like in the last lesson, we don't want to say all real numbers or all ordered triplets or anything like that because that's not the case. We're just going to say, hey, there's an infinitely many number of solutions. That's it.